Welcome to Lesson 10, Part 5, and this will be the last video of the lesson. We're going to examine water quality and how it's simulated in the EPANET software. Brief review of the theory of advective transport, decay reactions, and then in the practice it's used for estimating water age in the system, estimating the concentration of a constituent at different points in the network at different times, and can be used to help design responses to system intrusions or repairs. So in EPANET, transport is by Lagrangian approach. Probably a better term is discrete parcel advection. And then there's a mixing that goes on in tanks, and then there's actually decay that goes on in at the bulk of the material as well as wall reactions. So advective transport is the transport of dissolved or suspended material by motion of the host fluid. It requires knowledge of the fluid velocity field, which is the velocity of a fluid particle. Interestingly enough, that's actually quite straightforward from the EPANET hydraulics because you know the directions by virtue of the shape of the pipeline, and you can compute the velocity from the computed flow rates. So let's just examine a segment of pipe of length L, cross-sectional area A. The total volume contained in that pipe is L times A. The flow rate passing through is Q. If we take an entire segment and have it translate its entire volume out of the segment, the time interval that takes is simply the length times the area divided by the flow rate. And that time is a important criterion. The distance, look at this picture on the right. Has a marker, a green marker at the beginning at time equals 0, and as time progresses as fractions of this delta t, the green marker translates in this drawing from left to right, and when one delta t unit has elapsed, the green marker that was initially on the left has just left the pipe segment. The apparent speed of which that occurs is the discharge divided by the area. So the speed of that green marker is u, and that would be called the mean section velocity, or the marker velocity. Also notice in the diagram, we initially marked all the water in red, and we're displacing it with blue. So over time, the net mass of marked water in the segment changes. In this case, it's being displaced by blue, so the mass is decreasing in that segment. If we were to look at a different way of doing that in terms of masses, we would have the following diagram here is trying to depict that. Suppose that one blue volume enters the pipe segment. The mass of blue per unit volume of the segment is the concentration of blue. And if we let one pipe volume enter the segment, then the total mass of blue in the segment is concentration times fluid volume. And the rate of blue entering the segment is the mass per time. In terms of arithmetic looking things, the mass of blue is the area times the length times the concentration of blue in the segment. The rate of change of blue mass with respect to time is area times length times the concentration of blue times discharge divided by area times length. And so what we have left is the mass flux is concentration of blue times the flow rate. If we now considered a small portion of the pipe, we can look at this segment has length delta L, and we have the upstream face 1, downstream face 2. The mass flowing into that segment is C1, Q1. The mass leaving the segment is C2, Q2. And the rate of accumulation of mass inside the segment is the time rate of change of some concentration times the area times delta L. We can use these principles and write a balance equation for the segment. So we have C1 Q1 minus C2 Q2 over A delta L is equal to the time rate of change with this concentration in the segment. We can substitute the definition of average linear velocity for Q and A, and we have C1U1 minus C2U2 over delta L equals dC dt, and then we can take the limits as the size of the segment becomes very small, and we have minus D UC by dl equals dC dt, and this is a convective transport equation. Another way of writing it is shown here. The divergence of the mass flux is equal to the rate of change in concentration at the point. There's an obvious dependency on the velocity field, and to compute any mass fluxes we first have to have the velocity values. So if we take that previous problem setup and cast it in the structure shown here, water at a constant velocity is flowing through a zone carrying some dissolved component, concentration C0. There's no degradation of component, no dispersion, no interaction with the solid phase. The zone translates in space at a rate determined by water velocity. Contaminants dissolved does not alter density of flowing water and is soon to be uniformly mixed in the contaminant zone. Then an analytical solution for this is as follows. The equation of mass transport is this advection equation. The initial conditions of this segment are listed here. The boundary conditions in the source area are listed here. And the solution is that the concentration at any point in space at time is equal to 0 when that point in space is smaller than Vt minus L. Think of it as to the left of the zone. It's equal to C0 when the spatial location is in the zone, and it's equal to 0 again when the distance is beyond the travel distance at any moment in time. We could code that into a spreadsheet or build it into a series of small segments as depicted here, and using a cell balance approach. If we assume that time equals 0, the concentration in the inlet cell is C0, and we want to determine the concentration in the pipe segment at future times, we would assume the velocity is identical throughout the column or piece of pipe. Simple modeling approach is to teach each cell as a completely mixed reactor, and that means the concentration at the cell exit is identical to the concentration in the cell. With those assumptions, or those stipulations, we can come up with difference equations that relate the change of concentration in each cell to the concentration entering the cell and the mixed concentration within the cell. So cell 1, we know the amount entering is C0 because that's a given, and we can calculate the change in C1, the change in C2, C3, C4, and the change in concentration is simply delta T times this formula divided by delta L. The delta T over delta L multiplied by the velocity tells us how far a marker moves in a particular unit of time. Again, we could build a spreadsheet case, and we can also look at some other ways of visualizing it. They all have the same resulting governing equations. It's the same as before. Now let's get to EPANET. So that was just a very rapid background in advective transport. The key things to keep in mind are that we're moving things as parcels, moving from cell to cell to cell, or moving from a subsection of pipe to another subsection to another subsection. And by knowing the velocity and the initial concentration of things in the parcel, we can perform the following transport equations. So EPANET's water quality simulator uses the Lagrangian time brace approach to track the fate of discrete parcels of water as they move along pipes and mixed it together at junctions between fixed length time steps. The water quality time steps are much shorter than the hydraulic time step. So our hydraulic time steps in our extended period simulation were 1 hour, at least in the examples we've done so far. The contaminant time steps would be on the order of minutes, maybe 5 minutes or 1 minute. And that's to accommodate the relatively short travel times that occur within pipes. When the parcel concentration reaches a node, then there's multiple mass fluxes, and a flow-weighted mixing model is used to compute the concentration at that node. And bear in mind that node becomes a new C0 for any downstream link. So the concentration leaving a node is equal to the sum of the loads coming into the node, the Cn, Qn, divided by the total sum of the flows coming in. Tank mixing is handled by 4 possible models: completely mixed, 2-compartment, first in, first out, last in, first out. The completely mixed is just what it sounds like. Material constituent comes into the tank and is uniformly and instantly distributed throughout the entire volume of the tank. That's a reasonable approximation for small tanks or hydraulic time steps that are relatively long compared to transport time steps. 2-compartment mixing, the tank storage is divided into 2 compartments, an inlet outlet and a main zone. And when the inlet outlet zone, in terms of mass loading, becomes filled, then material spills into the main zone and vice versa. First in, first out mixing is a plug flow reactor, visualized as material comes into one end of the tank and translates across the tank and then leaves, and so there's no mixing per se. This parcel here remains its identity as it translates to the left. Last in, first out is a different type of plug flow. You can think of it as stacks of material entering, and then they leave the same way they came in. So the first material in, last material in becomes the first one to exit. That's a reasonable approximation for perhaps stratified flow in a tank. The other component in the EPANET water quality is a reaction component. There's 2 types of reaction schemes. There's bulk reactions, so that's in the water parcel or the bulk fluid, and wall reactions, that's at the pipe wall interface. This particular diagram here has iron 2. Iron 2 oxidizing to iron 3, and hypochlorous acid, perhaps from our disinfection process, is what stimulates the reduced oxidation state that interacts with iron 2 to create iron 3. It also acts with natural organic materials according to some different rate coefficient to produce disinfection byproducts. So those are the 2 reaction zones. The growth and decay of constituent bulk phase uses a choice of a no reaction, a zero order. No reaction would be like a tracer. Zero order kinetics, first order decay, first order saturation. Here's what the general advective fate and transport model looks like, and these are the different models, if you will, for these different kinds of reaction kinetics. An example of things that are modeled with these different ones, for example, first order decay is a model that would be useful for modeling the inactive disinfectant like chlorine. First order saturation growth, trihalomethanes, which is a disinfection byproduct. Water age is the case where the exponent here is set to 0, and Kb is non-zero. And then a tracer would be the N is set to anything, and the Kb is set to 0. Basically, it removes the term, the reaction term. Wall reactions are handled in a similar fashion in terms of the equation structure, and they're a secondary reaction term based on location in the network. Let's just do a simple example to see how you would build such a model. So here's our network, and we're asking the question, what's the disinfection residual in the system below if the source water has a disinfectant at 10 milligrams per liter, and the first order decay mass transfer coefficient, K sub B, is -5. Where we got the -5 and the 10 from is irrelevant at this time. They're actually invented numbers to illustrate how to parameterize the actual model. So to do that, we would build the hydraulic model, and here's an example of a hydraulic model that's been built. And this only makes sense if we're using time-varying demands, even if the demands don't change with time. So we're going to have a demand pattern associated with these models. Then we would select that there's a reaction and parameterize the reaction. set the total duration, and set the concentration for the entry. Run the simulation, and we can have it report values of the chemical concentration in the same way it can report pressures. And so we can get it at the node, and we see after, in this case, a long simulation, this node is the lowest concentration, and so the 10 parts per million coming in after the system has reached a concentration equilibrium, there's 4 parts per million at this location. Now, and if we have a target value at some nodes, say our minimum value for a particular situation is 5, and the maximum is 7, we could adjust doses or insert doses at different locations to keep everything between 5 and 7. And that would be how the concentration would be, how a model like this would be useful. We can use tracers to estimate water change in the system. In fact, tracer is a built-in component. You can use multiple sources to estimate mixing in the system. I have the word homework here. The way to do it in original EPANET is you would put a concentration to the source, get all the output, move that to a different source, and then from the two values of concentration from the two different simulations, you can mix those values and then determine the ratios of what came from which source. There's a multi-species extension that pretty much does all that for the analyst. Intrusions of contaminants can be modeled. You can inject a dose at a node and see where it arrives. So it's a fairly flexible tool for approximating water quality in a pipe network. So let's actually go through that last example live. So it's example 10. Save the bitmap. In the network, and it's not that I can't build the actual model quickly, but I think for the purposes of illustrating, it'll be far easier to simply have the data available. Okay, so there's the backdrop, and then we have the model. I'm going to turn off the backdrop, and we will examine parts of the model and then run it. First, we'll look at reservoir 9. This one has a source quality set to 13. I believe our example, this should be a 10. So I'll switch that back to 10. And our options, if we look at times, we see we have 24 hours, hydraulic time step of 1 minute, quality of 5 minutes, of 1 hour and 5 minutes respectively. The reactions are bulk reaction order type 1, bulk coefficient of -5, first order, wall reaction order is irrelevant because we don't have coefficients. So this is going to be a first order decay for the bulk. And in our quality, apparently I've named this particular material Freddy Krueger, and units are in milligrams per liter. And CFS and Hayes and Williams. Okay. So remember, we have to have multiple time steps for this to be functionally useful. We specify various reaction options as described in the user manual, and we can name our constituents. If we look at the demand pattern, it was incorrect. You don't need to have a demand pattern, but you do have multiple time steps. That's it. Let's run the simulation, see what happens. Okay, our run was successful. We're currently showing pressure and flow, and at the nodes we can change it to the Freddy Krueger value. And so at 1 hour, the 10 parts per million has only traversed to these 3 nodes. So it's somewhere between, if you look at the flow arrows, there's somewhere in here is the non-zero concentration. If you think of those parcels, there's a concentration front somewhere in here, somewhere in here, and somewhere in there. By the next hour, those concentration fronts have arrived here and here. Let's go ahead and look at velocity. And there's why they moved remarkably fast, because this is a very fast velocity section. The green ones are somewhat slow. Concentration front that was between here has now traversed down that way. This one's made it over to here. And again, on this pipeline, there's some concentration front somewhere here, and there's someone here. Next hour, we now have our every node has non-zero constituent except this node right here, junction 6. But by the 4th hour, junction 6 is now non-zero. Early arrival just occurred. By the 5th hour, it's at 4.12 and stays that way indefinitely. So that's how to model a constituent. Now the constituent could simply be age, and I believe that's built in. We're going to go take a look at that, see if it is. We will save that for a homework assignment. You can look online to see how to do age. It's entered by setting some things in the options. And I believe that's well documented in the user manual. So that concludes part 5 of lesson 10. And so at this point, most of the EPANET capability that you'll need to do your exercise sets and your design project for this class have been presented. I'm not sure I ever did saving a file, but if you want to save a particular simulation, you choose Save, and there's 3 file types. There's .net, that's a binary file, so that's only readable by the interface. There is a network file, which has file type INP, means input. That's an ASCII file. You can read that in a text editor. And there is a report file, the extension's RPT. That's also an ASCII file. So we can save those, and we will go take a look at those files, and then that will complete the lesson. So the input file, I'll open it with a text editor. There's what a EPANET input file looks like. Now this file can be emailed to someone else that has EPANET, and they can run it. It can also be uploaded to some online versions of the program, and they can run it that way. Here's the report file. Also open that with a text editor. And generates the report. It tells you the run date, the file name, and reports back the various information as of water quality at the different nodes at different times. So that concludes lesson 10. Thank you for your